Hey guys, in this relatively short video, we will be covering the photoelectric effect and its implications. So, around around 1900, it was discovered that if you shot a light beam at a thin metallic plate, then the electrons on the plate would get bounced off. So the light just comes in, applies the force, and bounces the electron off, where the force is calculated by the change in the momentum with respect to time. So light was like a ping pong ball or billiard balls. It could knock off electrons off that metallic sheet. And fast forward some time, maybe like 1910-ish, Einstein discovered that, hey, this photoelectric effect, maybe it means more than just knocking the electrons off. Now, Einstein did not discover the photoelectric effect. He didn't discover that. He just discovered what it implied-ish. And I'll dive into that in one moment. So, the energy of a photon is given by this equation over here. Energy equals Planck's constant times the frequency, and we already gone over Planck's constant in our last video. A equals 6.626 times 10 to the minus 34th. Okay. Now, there's nothing weird about this equation. There's no quantization. There's no quantization. And what does quantization actually mean? What does that mean? Well, quantization means that you can only have a certain quantity of something. So if I can only have 1 joule or 2 joules or 3 joules, just any n number of joules, where n is a natural number from 1 and so on, then my value of energy is quantized. However, if I can have 1.003 joules, 1.0910 joules, if I can have any continuous number of joules, then my value is not quantized. This equation over here, there is no quantization because it isn't quantized at all. There's no, you can have any amount of energy that you please with this equation. Just know that. So what happened was that Einstein looked at this picture over here, and he said, hey, light is able to knock off electrons. If you had a normal wave to knock an electron off, it would have to be very, very thin, very, very localized in order to knock that electron off. It has to be very, very thin, very, very, very localized to knock off that electron. So Einstein said, okay, it's almost like this light beam is a particle. And this sounds stupid. Of course light's not a particle. Light's a wave. But Einstein just said, hey, a light is kind of acting like a particle because a normal wave wouldn't be able to knock off electrons at an exact angle. Because waves are spread out. Spread out things cannot hit one point. But light can. So it's almost like light's a particle. This does not actually prove that light's a particle. There's no proof that light is a particle. This just suggests that light is a particle. It's evidence that it's a particle. But there's no proof just yet. And this realization by Einstein actually got him the Nobel Prize. Now, really, you could argue that this prize was actually for general relativity, and was masquerading as, sorry. You could argue that this prize was, yeah, was for general relativity, but it was just masquerading as the photoelectric effect, because at the time, GR wasn't really settled yet. It was still debated among scientists. So yeah, that's the story of the photoelectric effect. Light is still a wave. It just gives insights on maybe light as being a particle. It just shows that it can kind of behave as a particle, but there's no proof that it's a particle until we hit our next video. It's gonna be a good one. Have a great day.